You all should be able to do this by now. Okay, Christian, you're up.
Input sine is the measure of the angle swept counterclockwise from 3 o'clock position.
Measure of the angle swept counterclockwise from 3 o'clock. And what unit of measure is that? Right, any angle measure. So we can use degrees, radians. Okay, the measure of the angle swept counterclockwise from 3 o'clock. The amount of openness, right? The amount of openness. Opening counterclockwise. Okay? So it can be radians, degrees, grads, just as long as if you're using a calculator, your calculator's on the right setting, or whatever the context is, you know what you're measuring your angle in. Okay? Output. Margarita. Okay, vertical distance from the horizontal diameter. So we want to be a little more precise. We got to define positive and negative, right? From doesn't tell us what's positive and what's negative. But that's still above or below, so still the same distance from, right? So, and then what about the unit? Radius length, okay? So want to try it? Michael. Right, so it's the vertical distance above, right? So we got to say above so that we know that that's positive and below is negative. Above the horizontal diameter, and then we measure that as a fraction of the radius, Radius length, sorry, radius length. It's a fraction of the radius length. Okay, and we know that's the y-coordinate. So if we have a unit circle, or any circle, right? And we're measuring any circle in radius lengths. We're measuring, so it's always 1 unit away from the center is the circle. Then it'd be the y-coordinate of that circle. Okay, cosine. Input, exactly the same. What's the output of cosine? Let's see. Eric.
The horizontal distance to the right of the vertical diameter is a fraction of the radius.
Right, good. Horizontal distance to the right of the vertical diameter as a fraction of the radius length. Okay, and so again, this is going to be part of your quiz, is to write out these definitions. And it's not just so you can get points on the quiz. The whole point that I'm emphasizing it and making it, so putting so much importance on it, if you understand the input and output of sine and cosine, then you understand sine and cosine. People who really understand the input and the output, that it's a function acting on angle measure and giving these distances on the circle measured in a fraction of radius length, then you get it. And then you can apply that to so many problems when it comes to trig. Okay, and that's the goal, is to then take these meanings and to make sense of problems and to make progress on problems rather than having some kind of memorization approach. Okay? Okay, and we know that the cosine is the x-coordinate. Okay, so the second part of your quiz, I'm going to give you this blank circle, and you see that on the outside here, you have places to put all the coordinates of the points. On the inside, closest to the circle, all the radian angle measures, and then a little bit further towards the inside, all the degree angle measures for our 16 key angles. Okay, so just to practice this. So it all starts with that halfway around the circle is a pi radians of openness. First do fourths. Divide up the top half of the circle in fourths, and then all you got to do is count. You just count around the circle in pi over fourths. 1, 2, 3, 4, 5, 6, 7. Ready? Here we go. 1, 2, 3, 4, 5, 6, 7, 8. You just count. You just count. 1, 2, 3, 4, 5, 6, 7, 8. And then that gives us 4 new angles. The ones that split the quadrants in half. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Same thing for the sixths. Now you divide up the top half of the circle, or 1/2 of the circle, maybe, oh here, into 6 equal. So we know pi is half of the circle, so we're going to divide that up into 6 equal pieces. You just start counting pi by pi over 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's counting by pi over 6. Of course, we have the 4 that we already know, top and bottom, left and right. And then there's 4 here, the ones 2 pi over 6, 4 pi over 6, 8, and 10. That simplify to pi thirds. So all you need to do is count by pi over 4, count by pi over 6, so 1, 2, 3, 4, 5, 6, etc. And then on the pi over 6s, these 4 angles can simplify into thirds. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. And of course, we already had the pi over 2, pi, 3 pi over 2, and 0. So degrees is the same, so it's just a matter of, again, dividing by 4 and dividing by 6. What is halfway around the circle in degrees? Halfway around is 180. So first we can write, this is 90 up here, 270, 360. And then we're going to start by dividing by 4. So 180 divided by 4 is 45. And then 90. And then you could take 3/4 of 180, or you could just keep adding 45. Just keep adding 45 as you go around. So this is 135. Plus 45, 180. Plus 45, 225. Plus 45 is 270. Plus 45, 315. Plus 45, 360. So for the pi over 4s, you're just adding 45 degrees, which is the equivalent angle. Just keep adding 45 as you go around. What's 180 divided by 6? 30. So you just keep adding 30. 30, 60, 90, 120, 150. Just keep adding 30. 180, 210, 240, 270, 300, 330, 360. There are your degrees and radians. Okay, then if you watch the extra video, we derived in class that at pi over 6, the cosine's radical 3 over 2, the sine is 1/2. At pi over 4, they're both square root of 2 over 2, and then pi over 3, this cosine's 1/2, and the sine is radical 3 over 2. Because of the symmetry then, so here's looking at those ones that have 3 in the denominator. All of those sines and cosines will be 1/2 or radical 3 over 2. You just have to apply the right positive or negative. Okay? So what is the sine of 4 pi over 3? What's the sine of 4 pi over 3? So because it's below, it's in the third quadrant, we're below the horizontal diameter being negative, so negative what? Sine. Negative radical 3 over 2, right? It's going to be the same as sine pi over 3, but the opposite of it. This distance right here. Okay? What is the cosine of 5 pi over 3? What is the cosine of 5 pi over 3? going to be the same horizontal distance as pi over 3, and then we have to decide, is it positive or negative for cosine? Positive, it's to the right. It's to the right of the vertical diameter, so the cosine of 5 pi over 3 is 1/2, the same as cosine of pi over 3. So you can get all 16 angles with that kind of reasoning, right? We've got the coordinates by symmetry. We've got these coordinates in the first quadrant. We just had to apply the right positive or negative sign, where for sine, positive is above. So what quadrants is that? Sine is going to be positive in quadrants 1 and 2, and the sine is going to be negative in quadrants 3 and 4, or the y-coordinate, and then cosine is positive in 1 and 4, negative in 2 and 3, because that's to the left of the vertical diameter. So using that symmetry and using these sines and cosines in the first quadrant, we can get the sine and cosine of all 16 key angles by just applying the right positive or negative sign to those values. Okay, does anybody have a question about that? So you just need to have some system to fill out the blank circle with all 16 radian angle measures, with all 16 degree angle measures, and with all 16 coordinate pairs. And that will be on your quiz Friday. And I'll post the quiz like normal, okay? All right, any questions on that? So then what happens is, for some students, we learn these 16 key angles, and it's like, then these are the only 16 angles. How many angles are there from 0 to 2 pi? An infinite number of angles. These are just the nice, based on symmetry, these are the nice angles that break up the quadrants into 2 equal angles and to 3 equal angles. But between 0 and pi over 6, there's an infinite number of angles, all of which have an x-coordinate or a corresponding x and y coordinate on the circle, so cosine or sine. So just because we're now kind of focusing on these 16 angles, don't lose sight that these aren't the only angles, right? Yeah.
It's like on the homework class, well, that is day to day.
Yeah. Maybe. Okay. We made it. Okay. So here we go. So we're twirling this ball at 2 radians per second, and it's going to start from. We're going to start the clock at the 3 o'clock position, and they're asking to write theta in terms of t. So theta in terms of t. So does this mean we're going to have theta equals some expression of t's, or are we going to have t equals some expression of thetas? First or second? So if we have theta in terms of t, then we want theta equals some expression that has t's in it, that if we plugged in a time, it would give us, it's kind of a function idea, if we had a time, it would tell us the angle that's been swept in that number of seconds. Okay, so some of you may be able to just come up with this, but if you can't, here's a strategy that should all come to mind, that should be able to think of and use, and that is to make a table. So when t is a certain value, what's the corresponding theta? So at t equals 0 seconds, what angle theta has been swept out? 0. After 1 second, if it's going 2 radians per second, after 1 second, what angle? Should make sense. 2 radians per second means every second it sweeps 2 more radians of angle. So what about 5? After 5 seconds, 10 radians. After 30 seconds, 60 radians. So setting up a table like this and observing the pattern then will allow you to generate the general formula. If every t seconds that goes by, what angle in radians is swept out? 2t. And so this is a strategy that you should be able to use and invoke. If you're trying to write a formula and you're not sure what that formula is, create a table of values and look for the pattern. So theta equals 2t. Okay, so now I'm showing a graph here, and I will tell you that this right here, oh, it's out of the way. It's not. Okay, there we go. So now I'm showing you a graph related to the ball's motion. And I'll tell you right now that this on the x-axis is 2 pi. So, and then this is 0. So what is implied about what quantity am I showing on the horizontal axis there of our graph? What quantity am I showing? Okay, it's measure of the angle, right? It's measure of the angle. Measured in? Okay, so this is theta in radians. Okay, and so if I came up here and said this was right here, let's get out of the shadow here. If I told you this was 1 and this was -1, then we could kind of deduce what quantity I'm showing on this graph here, what quantity I'm showing on the vertical axis. So what quantity am I showing on the vertical axis? All right, he wants horizontal distance. Is it showing horizontal distance? So when the radian is 0, what is the horizontal distance? What is the horizontal distance when the angle is 0? 1, right? 1 full radius length to the right. And is that what this graph is showing? Yeah, it's showing that when the angle is 0, by the vertical axis on this graph, it's showing the horizontal distance on the circle. And then as the ball swings up to an angle of pi over 2, what's the horizontal position? Right here? Is that what the graph is showing? Okay. What angle is this? What's the horizontal position? I can't hit it exactly. That's as close as I can get. All right. So for an angle of pi, horizontal distance to the right is -1. That's what we're seeing right here with this point right here. Sorry. And then the bottom of the circle, angle is 3 pi over 2, or 1.5 pi. Horizontal position is 0, and then when it gets back to the starting point, it's swept 2 pi, and the horizontal distance to the right is 1 radius length, 1 full radius length. Okay, so what graph is this? The graph of sine. Cosine, right? If we're tracking horizontal distance as the angle increases, we're tracking the sine wave. Tracking the sine wave. Right? Cosine. This is cosine. All right, this is cosine. What would happen then so this ball keeps swinging around and around? Are there angles greater than 2 pi? So we focused on 0 to 2 pi, but can you have an amount of openness bigger than 2 pi?
Yes.
Sure. In fact, you can have any real number can be an amount of openness. You just keep rotating. You just keep going on and on and on. So when it hits 2 pi, we start here. One more full rotation would be from 2 pi to what angle measure? 4 pi. And what would the graph look like if we were to keep going from 2 pi to 4 pi? it'd be the same profile of output values repeated, right? Because it just, once it starts to circle a second time, all the horizontal distances are the same for the second rotation. So from 2 pi to 4 pi, we'll have a repeat of this. So this is called one cycle, because after one cycle, and it starts over. So this is called one cycle of the graph, what I'm showing. And what interval of input results in one full cycle of output values? What interval of input? Get this right. So what is our interval of input that results in one full cycle of output values? So I should say maybe the the width of the interval. So as a single value, how much input, or what length of interval of input results in one full cycle of output values in this case? 2 pi, right? So every time you go 2 pi and you do it again, you're going to get the same cycle over and over again. And there's a name for that. There's a name for it. So I took the time to write out this precisely, the interval of input that results in one cycle of output values. Some of you might know what that name is. What is it? Not the frequency. This is called the period. Period is how much input needs to go by, or the interval of input that gives one full cycle of output values. And then it starts over. So what is the period of cosine? What is the period of cosine? What interval of input gives us one cycle in cosine? 2 pi. This is really important because every other period that we get related to cosine and sine is going to be based on the original cosine curve that has a period of 2 pi. So this is important that you can articulate what the period is. It's the interval of input that results in one full cycle of output values, and that is 2 pi. Okay, so this function that I've graphed here, I'm showing in blue. If we wrote that as, say, f of theta, how would we define f of theta? It's just cosine theta, right? Because the input is the angle swept counterclockwise from 3 o'clock, and the output is the horizontal distance to the right of the vertical diameter in fraction of a radius. That's cosine theta. So what if we wanted to come along now and make a new function and write the same function in terms of time? Okay. Exact same situation, but a new function that gives me, this is still going to output the vertical distance horizontal distance in fraction of a radius length, but now the input would be time. So I want the same output, but I want my input to be how much time has gone by. So it'd be cosine of t. Okay, so I'm hearing t and 2t. Okay, so what does cosine receive? What does cosine take and operate on? What's the quantity that's the input of cosine? Theta, angle measure, right? Angle measure. So it still always will, whatever number you give cosine, it's going to think of it as angle measure swept counterclockwise from 3 o'clock. So we still need to put that in. What is it? 2t. because whatever goes into cosine has to be the angle swept. Okay, so now if I wanted to graph g of t, what would change? Would my vertical axis change? No. But horizontally, I'm going to come up here and say I want to graph how many seconds. So now if we talk about the period of g, that's going to be the interval of input. What's our input of g? T is the input. So now we want the interval of t that's going to give one full cycle. So in order to find that, we use the period of cosine. So if Tp, say that's the period of g, then what does 2t need to reach in order for cosine to have a full cycle? 2 pi, right? So because this is our angle theta. So we're going to take our angle theta. When our angle theta reaches what? When it reaches 2 pi, then we'll have a full cycle. So we're looking for what? We're looking for the time such that the angle reaches 2 pi and therefore the cosine starts over again. So we're going to take that angle and we're going to set it equal to 2 pi. So this is a really important thing that you have to understand and be able to do. And that allows us to find the period of the g function, which is a time period. And what is that time period? So what would the period be in terms of time? Yeah, we just solve for it, and we're going to get 2 pi over 2, or pi. All right, so it takes pi. If we're going to do this, our horizontal axis of this graph in seconds, then our period is pi. And so then what is, and we're always going to break it up into fourths because of the 4 quadrants. What will be half a rotation? How many seconds will it take? Pi over 2. The first quadrant of a rotation will take how many seconds? Yeah, so you can you take your period and you divide by 4. And then you can just add pi over 4 each time, or you can take half of your period and 3/4 of your period, however you want to do it. But figuring out these, dividing the period by 4 is that's what we're gonna do a lot, all right? So we start with your period, divide it up into 4, representing the 4 quadrants of the circle. And those are kind of the key points on the curve. Okay, so if we're graphing g, then our axis scale would be in seconds, and our period would be pi, based on this. Okay, so how about this situation here? Twirling this ball at 2 radians per second. Notice anything? So imagine that you're doing it. What's that? Realistic? Why not? It's too slow, right? Imagine trying to twirl a ball and keep its radial speed constant. 2 radians per second would be really tough. This is super slow. So let's speed it up a bit. And let's speed it up to, I think there's an example in there, 9.7 radians per second. So this feels more realistic. This is something you could get this going at about this speed and keep it kind of constant like this. Okay, so now we're gonna they often use omega to mean radial speed or radians per second. So omega 9.7 radians per second. So I want you to find the period and write a function h of t for this new radial speed. So find the period and write h of t. That's going to output horizontal distance in fraction of a radius length for an input of t seconds. Okay, go, do that. Oh, and before that, you need to write theta in terms of t. So first write theta in terms of t, determine the period, write h of t. If omega is 9.7 radians per second. Okay, Alex back there. His headphones are too loud. Alex, take your headphones out. Come to class. Isn't that Alex? Who is that? Yeah, or not. That's not. Josh. Sorry, Josh. Alex isn't here. He sits up there, though. Okay, Josh, tell me. Theta equals? Was it? 9.7 t. For every 1 second that goes by, this thing goes 9.7. So in t seconds, it'll go 9.7 t. Okay? How do we find the period? How do we set up finding the period? Jed?
We put 9.7 TP is equal to 2 pi.
What does 9.7 TP represent? Nope. It doesn't. What quantity is 9.7 TP? What kind of quantity is that? Yeah, it's angle, right? It's an angle, 9.7. Specifically, if t is the period, then specifically what angle measure is that? That's what Jad said. Yeah, so if we want the period, the time period, then the corresponding angle has to be 2 pi, because we know 2 pi gives us 1 period of cosine. All right, so over here, so what is that? Is that like 0.648? If I remember that right? Okay, so then in red, if we're going to do it with spinning 9.7 radians per second, then our period is 0.648. Okay, what is the function? Nick?
I'm not sure.
If we want the output to be horizontal distance to the right of the vertical diameter, what kind of function should it be? Cosine. And then what goes into cosine is always angle measure. But our input is t. So what angle measure do we have in terms of t? 9.7 t. So then we would divide this up into 4. We'd have to take 0.648, divide by 4 to get the key times throughout the first cycle. In seconds. Divide by 4, divide by 2, 3/4 of 0.648. Okay.